Hi everyone. In this video, we will begin our discussion of series of real numbers by looking at their connection to sequences of real numbers, which we discussed in a previous video. So to begin, we first want to define what we mean when we say the word series, or we may also sometimes refer to infinite series. So for any sequence a sub k, we can form a sequence of partial sums which is formed by simply taking the sum from k equals p up to n of that sequence. So, for example, right, you sort of imagine you have a sub k is equal to 1 over k. So your sequence looks something like 1, 1/2, 1/3, 1/4, so on and so on. Okay. And from that sequence, we could form a sequence of partial sums. Now, in this particular case, we can do this for any fixed integer value. I'm going to do it just starting with 1. So I'm going to define this to be k equals 1 up to n of a sub k. But right, note that what this really means is this is just a 1 plus a 2 all the way up to, right, the nth term. So if I were to start writing out the terms of this sequence S sub n, this sequence of partial sums, the sequence of partial sums of this sequence AK. So the first term is the sequence of partial sums is just the sum of the first one terms. So it's just the first term. The second term in the sequence of partial sums is the sum of the first two terms. So it'd be 1 plus 1/2, which is 3/2. The third term in the sequence of partial sums would simply be the sum of the first three terms. So I would be looking at 1 plus 1/2 plus 1/3. So in terms of, I think, sixths, let's see, this would be 9/6 plus 2/6 would be 11/6. And we could keep forming this sequence in another way. So just backing up, we started with a sequence AK. From that sequence, we're constructing this other sequence, the sequence of partial sums. Okay. Now, we can think of this sequence of partial sums really as being the series itself. Okay. But often when we're talking about series, we often express it in this form here, this sort of infinite sum form. And if you go back to Calc 2, right, in Calc 2, you probably looked at things like, uh, maybe something like this. I don't know. There's a series, right? And you answered questions about whether this series converged or diverged by applying some appropriate tests, convergence tests, and we'll talk about those. But right now, our goal really is to understand how we should think about series, right, in order to be able to prove things mathematically. So while, yes, we think about them as this infinite sum, formally, really the series is identified by the sequence of partial sums, right? So the sequence of partial sums really is the series, right? And then understanding whether a series converges or not is then just the same thing as understanding whether the sequence of partial sums converges. So often when we talk about the infinite series, we're usually thinking about a representation that looks something like this, right? Sum k equals some number up to infinity of the terms a sub k. But that's equivalent to thinking about this sequence of partial sums. And so the infinite series will converge if and only if this sequence of partial sums converges. And that's really because they're really exactly the same thing. An infinite series is really just a sequence of partial sums. Now, why do we have this distinction, right? Why do we have this? Well, historically, right, people were thinking about series and sequences as sort of separate things or unrelated, or at least the applications of them weren't necessarily related. And it wasn't until later on, as mathematicians are trying to unify some of the theory behind this, that it comes to be realized that, oh, we should really probably think of these series things in terms of sequences. And so you get some terminology that's a little bit confusing, right? Like, what is the series? Well, the series is really the same as the sequence of partial sums. Those are really the same thing. Um, but we have two words that sort of mean the same thing. Now, from our perspective, we've already proved all sorts of things about sequences. So what we want to do is just use what we already know about sequences to help us prove things about series. Now, we'll see in today's video that we can go ahead and do some of that, but it will also be important to recognize, series are a special form of sequences, and so it might be nice to have some specialized theorems to help us with those as well. If this series converges, this value S that it converges to, so whatever the series converges to, the sequence of partial sums converges to, we call that the sum of the infinite series, right? So once we know it converges to some value, and we call that value the sum of the infinite series. Now, we want to start by just looking through and looking at some examples of infinite series to just observe some of the different kinds of behaviors we're going to have to contend with as we explore series a bit more. So I want to start with actually a series. So we have sum k equals 1 to infinity of -1 to the k plus 1. Now, it is true that we sometimes think about series as just sort of infinite sums. And in fact, historically, right, that's exactly what series were arising from. But it's also important to recognize that there are some limitations to that, or even if not limitations, it can draw us into some incorrect reasoning. So if I were to think of this as sort of an infinite sum, right? I might say, okay, when k is equal to 1, I'll get -1 squared, which is 1. And then when k is 2, I'll get -1 cubed. So that's a plus -1 or -1. And if I just write out the terms, I'll get this. So on and so on. Now, when I express it in this form, I'm really tempted to do the following. Really tempted to just go, oh, let me just group these like terms together. I mean, I could keep sort of doing this forever, right? And then I say, well, each of these adds up to 0. So just get a bunch of zeros. Okay, this must equal 0. Well, it actually, you could do that and go, okay, yeah, maybe that seems okay. But you might pretty quickly realize that there might be some sort of problem here, because if I group them differently, so if I had grouped like this, then what I would be left with is I would be left with a 1, and then in each of these green brackets, I would have a -1 plus 1, -1 plus 1, each of which would add up to 0. So and so on. And so I get that this is equal to 1, and of course, hopefully that seems problematic to you, right? Because these two things are not equal to each other. Okay, so the question is sort of, what am I doing wrong here, right? Why isn't this working? Well, there are a couple of answers, and perhaps the most important is simply that you can't just think of this like a normal sum. So this is a series, and even though we think of it as sort of an infinite sum, we have to be careful, because when we're doing all of this grouping here, what we're really doing is applying properties of associativity of addition. And so we know, of course, that a plus b plus c is equal to a plus b a plus c, but that holds for finite sums. Here, this is not a finite sum. Again, you can think of it as an infinite sum, but it's really just a series, right? That's what an infinite sum is. It's a series. So here, what we have to do is we really have to go back to the definition and ask ourselves, well, okay, what does all this stuff really mean? Okay, so if I come back here, right, this is like my a sub k here, right? These are the terms, and I want to think about what's that sequence of partial sums going to look like. So if I start to write out this sequence of partial sums, okay, well, what is the sum of the first one term? Well, the first term of this, when k is equal to 1, is 1. Okay. What's the second term of the sequence of partial sums? Okay, so again, just maybe to help us out, right? If we just write out here the AKs, right? The AKs are just going 1, -1, 1, -1, so on and so on. Okay, so the sum of the first term is just 1. The sum of the first two terms is 0. The sum of the first three terms is 1. The sum of the first four terms is 0. Sum of the first five terms is 1. Sum of the first six terms is 0. So on and so on. And so what we observe here is this sequence of partial sums, which again, really, this is the series. And then I ask myself, well, is this sequence of partial sums converging? Well, no, it's alternating back and forth between 0 and 1. This sequence never converges to anything. And so this series, which again really is the same as the sequence of partial sums, this series does not converge, it diverges. So already we see here, I mean, from a fairly straightforward example, right? I mean, there's nothing weird going on here. You're just adding together 1, -1, 1, -1, 1, -1, 1, -1, right? We see that we have to be very careful in how we think about these series, right? Yes, we do want to sometimes think of them as infinite sums, but we have to be very careful to recognize that when we say infinite sum, it's really not going to behave like a sum in a traditional sense. Now, what we'll see later on is that there's a very special class of infinite series where you can apply things like associativity and commutativity, and there's some series that have some really nice properties. But not all series have those, right? So we have to be careful about how we apply that. All right. So already, I think an important thing to have as a student of analysis is a toolbox full of examples, right? And particularly examples which make you maybe a little skeptical, right? Which give you pause when you start to make claims that maybe aren't totally true, right? And this is a really good first example of that. Um, let's look at another example. So here I have the sum k equals 1 to infinity of 1 over k. Now this series, in fact, has a special name. This is referred to as the harmonic series. Okay. And so again, if we look here and think about, right, our AKs, right, just the terms in our series, right? So these AKs, these are just 1 over k. So 1 over 1, 1 over 2, 1 over 3, 1 over 4, so on and so on. Okay. And as we saw before, right, I could start thinking about the sequence of partial sums. So, right, if when I did that earlier, right, we get 1, we get 3 halves, we get 11 sixths. Then you could add a fourth. So this would be 44 24ths plus 6 24ths would be 50 24ths or something like that. Okay. Um, and this will already give you a pretty good idea. I mean, if you look at the terms here, like even just the first few, so this is like 1, this is a half, this is a little bit less than 2, this is just a little bit more than 2. And you might start to feel like, okay, this is really slowing down, right? These are probably leveling off at something, right? I mean, they're not growing very quickly, so probably maybe they're leveling off at something, right? Already, right? I mean, the difference between any two consecutive terms is certainly going to 0 because the difference between any two consecutive terms in your sequence of partial sums, excuse me, is just the term here, right? So like the difference between these two terms, so S4 minus S3, in this case, this minus this, is just A4, right? Because what was S4? S4 was A1 plus A2 plus A3 plus A4. S4 is A1, or sorry, S3 is A1 plus A2 plus A3. And so the difference is just this next term. So the difference between any two consecutive terms is just going to 0. Is that enough to say it converges? Well, the answer is no. It is not enough that the difference between your two, it's not enough for the terms of your series to be going to zero. That's the same as saying that the difference between any two consecutive terms in your sequence of partial sums is going to zero. And in fact, you can find many proofs of the fact that the harmonic series diverges. I'd encourage you to go to Google and type in proof that the harmonic series diverges. You'll find many, many, many proofs of this. The one we'll actually look at is due to one of the Bernoullis. So if you don't know much about math history or the Bernoullis, there were several different Bernoullis, two of which were brothers. I think this proof is due to one of the brothers, although I'm not entirely sure. But their idea is as follows. It originates with the observation of the following fact. So if I take some natural number c and I add up 1 over c plus 1 over c plus 1 plus 1 over c plus 2, and I keep going all the way up until I get to 1 over that number squared. Okay, so maybe off to the side here, just as an example, you can imagine like 1 over, 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8 plus 1 over 9. So this would be the example when c is equal to 3. Okay. So one of the things that he first observed, Bernoulli observed, was that if you could replace, so leave 1 over c alone, but then take all of the other terms and replace the denominators with c squared. Okay, so what you'll be doing is you'll be making each of these denominators larger. Well, not this one, it'll stay the same. But each of these denominators you'll be making larger by replacing them with c squared, which will make the whole expression smaller. Now, again, over here in our example, right, you're just replacing all the rest of these with 1/9. Now, if I then look at these terms, they're all 1 over c squared. So if I just knew how many there were, it would be really easy to add them all together. So I asked myself, well, how many are there? Well, these start at c plus 1 and go all the way up to c squared. So the total number of terms here is c squared minus c plus 1 plus 1. So it's the difference in between them. The difference in between them misses one of the endpoints, so you add back in a 1. So in this case, it just gives you c squared. If you calculate that, that's c squared minus c. Over here, where our c is 3, that should give me what? That should give me 3 squared, which is 9, minus 3, which is 6. Are there 6 terms here? 1, 2, 3, 4, 5, 6. Yes. Okay, so there's 3 squared minus 3, which is 6 terms there. Okay, so we did count that right. So down here, right, this sum is equal to this 1 over c is just hanging out. Plus down here, I have c squared minus c terms, each of which have the value 1 over c squared. So the sum in this box becomes this. Well, if I look at this, this is 1 over c plus c squared over c squared, which is 1, minus c over c squared, which is 1 over c. So this whole quantity turns out here to be 1. So what we've shown is we've shown that if you add up 1 over c plus 1 over c plus 1 plus 1 over c over 2, so on and so on, all the way until you get to 1 over c squared, whatever that quantity is, it will be greater than or equal to 1. All right. Now, how does this help us with our problem here about the harmonic series? So let's use that observation then to help us. So again, I've mentioned at times we'll want to sort of write this out and think of it as an infinite sum. This is going to be one of those times, but then we'll need to justify this in terms of partial sums. So if I just think about writing out terms here, and I think of this as a sum, okay, so I think about this as 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus, I'm going to use some judicious dots here. And now, and again, I have to be a little careful here, but let's put in some parentheses. Okay, right. Yeah, I was just saying we have to be careful about using associativity, but again, this is a little hand wavy, but we'll make it rigorous in a bit. My idea is that if I look at each of these, this is the sum 1 over c all the way up to 1 over c squared. So this quantity must be greater than or equal to 1. Similarly, this is a sum from 1 over c all the way to 1 over c squared. This must be greater than or equal to 1. Plug in your calculator. Right, 26 times 26, 6, bring a 3 up, 12, 15, put a 0, 52, 676. Okay, 26 squared is indeed 676. I actually just doubted myself for a minute. So this is 1 over c all the way up to 1 over c squared. So I ought to be able to sort of say that each of these is greater than or equal to 1 plus 1 plus 1. And I ought to be able to continue this process forever and ever, which seems to suggest that this ought to be greater than or equal to infinity, right? Which should mean that this diverges. Now, how do we make this rigorous? Well, what this shows us is that it's pretty easy to observe, right, just straight off the bat, that my sequence of partial sums, those will all be greater than or equal to 1 for all n greater than, sorry, my sequence of partial sums will be strictly greater than 1 for all n greater than 1, right? So here I'm equal to 1. For all the rest of them, I'll be greater than 1. Okay. Now, my sequence of partial sums will also eventually get bigger than 2. When will it get bigger than 2? Well, it has to be bigger than 2 by the time I get out past the 4th term. Right? All of my sequence of partial sums, right? The values in my sequence of partial sums must be greater than or equal to 3 by the time I get out past the 25th term. Okay. My sequence of partial sums must be greater than 4 once I get out beyond what? Once I get out beyond the 676th term. And now you could repeat this, right? So like so this will get bigger than 5 for all n. Now what's going to happen? So I'm going to go to the next one, which will be 677, right? I'll need to take that number and square it. Okay. And then this will get greater than 6 when, well, now let's see. I'm going to take the previous number, I'm going to add 1 to it, and I'm going to square that quantity. Okay. And so I could repeat this. I could always find some value n sub k so that s sub n was greater than k for all n greater than or equal to some nk, which means my sequence of partial sums eventually gets larger than any number you give me. That means that the sequence of partial sums is running off to infinity, which means that this diverges. So it's okay to use this notion of sort of an infinite sum to help you gain intuition. It's important, however, that when we want to rigorously prove anything about it, we have to go back to this idea of the sequence of partial sums. Okay. And in fact, if we really wanted to solidify this, what we'd probably do is a proof by induction to justify that we can always make such a choice here, right? That we can do this for every integer k. Therefore, our sequence of partial sums must be running off to infinity. All right. Let's look at one more example before we look at a few theorems. And in the last example, I actually want to look at one very special type of series. For those of you, some of you teach at the high school level. I don't know. We used to talk about these in high school. To be honest, I'm not familiar enough with the high school curriculum at this point to know whether these are necessarily still covered, whether they're covered in any particular state. Of course, I'm certainly not an expert on the curriculum across all 50 states or internationally. So it's certainly a topic that is accessible to high schoolers. And those are the particular type of series known as geometric series. Okay, so let's look at a very standard example of a geometric series. So this, again, is a special type of series called a geometric series. Geometric series are series whose terms have a common ratio. So if I look at any two consecutive terms, they have a common ratio of 1/2, right? So the next term in this series is 1/2 of the previous term. Okay. Now, this particular one is sometimes called Zeno's series. This, of course, goes back to Zeno's paradox. You may have heard this idea that you're running in a race, and let's just say you're going from 0 to 1, and that requires you to go halfway, and then halfway the rest of the way, and then halfway the rest of the way, and halfway the rest of the way. And Zeno's paradox was the idea that, or the sort of the question of, well, if each of these sort of can break this into an infinite number of segments, each of those segments must take me some finite amount of time, right, for some non-zero finite amount of time to cover. How could I ever possibly cover the entire distance? That was Zeno's paradox. But so this series is sort of like adding together the lengths of each of those little distances, little journeys. And so already you might sort of think, okay, it seems like this should probably be equal to 1. How would we prove such a thing, though? Before we prove it formally, let me give you one more sort of justification, maybe a little bit of geometric intuition for this. So imagine I took a unit square, okay, and in the first term of my series, if I just start writing these out, right, this would be 1/2, 1/4, 1/8, so on and so on. So if I come over here to this unit square, I could first represent a half by this area. So there's area 1/2 there. Okay. And then I could come up here and put in area 1/4 here. And then I could put in, say, an area of 1/8 here. And then, say, 1/16 here. Okay, and I don't want to belabor this too much, but let's do one more, right? So this would be like 1/32, and you start to get sort of some intuition that if I kept repeating this process, right, I would eventually fill out this entire unit square. The entire unit square has area 1, and this is areas of 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, so on and so on. So again, it seems like this ought to be sort of converging to 1. How do I prove this? Well, again, if I'm going to prove anything about these, I need to use the partial sums. Okay. Now, because geometric series have this nice property that they have a common ratio, we can play some algebraic tricks with them that we can't necessarily do with a general series. Okay. So what I'm going to do is I'm going to just think for a second, right? What is the nth partial sum, right? The nth partial sum is just the sum k equals 1 up to n of 1/2 to the k, right? I just add up the first n terms. Now, this is really a sum, right? Because it's finite, right? So this is a sum. I can use all my normal properties of associativity, commutation, like everything is nice here. This is a nice finite sum. Okay, so speaking of properties, let me just multiply this by 1/2. Okay, so if I were to multiply this by 1/2, right, I could just throw a 1/2 out front there. Um, but I could also distribute this right into each term. And again, this is a finite sum, so that's okay. That's something you can do. All right. So this would just be the sum k equals 1 up to n. So I would get 1/2 times 1/2 to the k. That would be 1/2 to the k plus 1. Okay. Now that looks fine. Now, one of the things you might notice is you can re-index this sum. Okay. So if I just let r be equal to k plus 1. My goal is sort of here I just have a single variable. I just want a single variable here. So let me replace this k plus 1 with an r. Okay. But then if I do that, my indices here are going to change. So when k is equal to 1, r is equal to 2. And when k is equal to n, r is going to be equal to n plus 1. Okay. But we should also recognize that, like, what I call whether I call this R or K, like, that doesn't really matter, right? It's just a dummy variable that I'm using to help index, like, which term is which. So, like, the fact that I had K here and R here really doesn't matter because, right, the first term of each of these is still both 1/2 squared, right? 1/2 squared, right? It's just here I'm writing 2 as 1 plus 1, and here I'm just writing 2. So it doesn't actually matter what I call this. I could, in fact, have just, instead of calling it R, I could have just called this K again. These still give me the same sums. All right, now why is that helpful? Well, now let me look at S sub n minus 1/2 S sub n. Well, S sub n is a sum k equals 1 up to n of 1/2 to the k. Whereas 1/2 S sub n is a sum k equals 2 up to n plus 1 of 1/2 to the k. So the reason I wanted to do this is, notice, like, the terms are the same here. It's just what values of the index we have in each one. So when k is equal to 3 here, I'm going to get the same term when k is equal to 3 here. So you notice a lot of these terms are going to cancel out. When k is equal to 2, these terms will cancel out. When k is equal to 3, they'll cancel out. When k is equal to 4, they'll cancel out. When k is equal to n, they will cancel out. But when k is equal to 1, I don't have a term here for this to cancel out with. And when k is equal to n plus 1, I don't have a term over here to cancel out with. So you're going to get a lot of cancellation here, except you're not going to lose the k is equal to 1 term here. And over here, you're not going to lose the k is equal to n plus 1 term. Okay. And again, because these are all finite sums, we can rearrange things, everything commutes, like all this cancellation works out just as it would for any normal sum, because these are finite sums. These are really sums. All right, so what is this really, right? This is really 1/2 minus 1/2 to the n plus 1. On the left-hand side here, what do I have? I have S sub n minus 1/2 S sub n. Well, that's just 1/2 S sub n. So now let me multiply each side by 2. So I multiply each side by 2. Multiplying this term by 2 will just give me a 1. Multiplying this by 2 will just give me a 1/2 to the n. And now notice that what I have here is a closed form expression for the nth term in the sequence of partial sums. So if you ask me now, hey, what's the sum of the first 50 terms here? I can tell you, well, it's 1 minus 1/2 to the 50th. Okay. What's the sum of the first 70 terms? Well, it's 1 minus 1/2 to the 70th. Okay. But the nice thing is, now I can take a limit easily, right, of this sequence of partial sums. This is just the limit as n goes to infinity of 1 minus 1/2 to the n. As n goes to infinity, this will go to 0, right? 1/2 raised to higher and higher powers is going to get smaller and smaller. So this just goes to 1 minus 0, which is 1. So now what have we done? We have shown that the sequence of partial sums converges to 1. That's exactly what it means for this infinite series to converge and to converge to a sum of 1. Okay. So again, in this very nice case of a geometric series, we can play this nice algebraic game. Now, if I gave you a different geometric series, you could do the same thing. You could play the same algebraic tricks. Now, you'd have to be a little more careful. Like, you're not always going to multiply by a half, right? In fact, you're going to multiply by whatever the common ratio is. So, if you had a different geometric series with different terms there, you would multiply by something else. But you can play sort of very similar algebraic games to conclude whether the series converges and to what value the series converges. All right. So we're not going to do this in the abstract. There's a proof in the book that does this for a general geometric series. But we will briefly just look at the result. This is probably something you also saw in a Calculus 2 course, right? And it simply says that if I have a geometric series of the form a times r to the k, and here, just to make this formula a little bit nicer, we're going to actually assume it starts at 0 and goes up to infinity. But this series converges to a divided by 1 minus r when the absolute value of r is less than 1. So this series converges if this r value is strictly between -1 and 1, and it diverges for every other value of r. Okay. Now, there is sort of a hidden technicality in here, which is that we should really assume, if we're talking about a geometric series, we should assume this a is not 0. If you assume this a is 0, then you just get the constant series 0, which of course converges to 0 irrespective of what r is. We really wouldn't consider, if a is equal to 0, we wouldn't consider this a geometric series anyway, because the ratio of the common terms would be 0 over 0, which is of course undefined. So again, we wouldn't normally consider that a geometric series in any event, but we are making this assumption that a is not 0. So if a is not 0, then this geometric series converges when the absolute value of r is less than 1 and diverges when this absolute value of r is greater than or equal to 1. Notice, in fact, if you go back, the very first example of a series we looked at, that -1 to the k plus 1, that is in fact a geometric series with r is equal to -1. We observed there that it diverged, and this result matches that as well. All right. Now, the last thing I want to look at is just to recognize that we can get some quick and easy results about series from the fact that a series is really just a sequence of partial sums. Okay. So this Cauchy criterion for series, this is a theorem which says that an infinite series, and notice here, I'm often, if it sort of doesn't matter what we're indexing with respect to, where I'll normally just write a generic sort of series here. I may, when the indices are important, I will, denote that, but otherwise, if I just say an infinite series and don't put any indices, you just assume it has an infinite number of terms and that it doesn't matter where I start at. Okay, so an infinite series sum of the ANs converges if and only if, for every epsilon greater than 0, there is a natural number capital N, such that whenever little n is greater than or equal to little m is strictly greater than n, capital N, we have this condition. Okay, the sum k equals m up to n of the a sub k's in absolute values is less than epsilon. Now this looks maybe strange, okay, but if we examine this term on the left-hand side, okay, what we see is that this is, in fact, if I think about, the sequence of partial sums, let me actually give myself, let's write this over here. If I think about sort of the sequence of partial sums S sub n, right, this would just be the sum, say, k equals some number p up to n of the a sub k's. I could also think about the m minus first. You might be saying, why are you, well, who cares about that? Just stick with me for a second. This would be the sum k equals p up to m minus 1 of a sub k. And now if I took their difference, right? And remember here, like this assumption is that n is greater than or equal to m, which means that n is strictly greater than m minus 1. Okay, so there are fewer terms then in this series than in this series. So this difference, if I look at the difference between these, this starts at p and goes up to m minus 1. This starts at p and goes even further than m minus 1. It goes all the way up to n. So when I take the difference, all the terms from p up to m minus 1 appear in both sums. They cancel out in the difference. The first place that I have a term here that doesn't appear here is just past m minus 1 at m. And the last term I get here is n. Okay. So this quantity over here, this is really just the absolute value of s sub n minus s sub m minus 1 is less than epsilon. So if this holds, then that means this is true, again, for all little n and little m satisfying, this criteria that they're greater than n. And if you look at this, this should look familiar from our discussion about sequences. This is just the definition of s sub n being Cauchy. So really, all this criteria is doing is saying, if we think about series, instead of thinking about series, we think about the sequence of partial sums, right? The sequence of partial sums will converge if and only if the sequence of partial sums is Cauchy, right? We proved that in the previous video, okay? Well, now what we're saying here is just that, well, that saying that the sequence of partial sums is Cauchy, that's really equivalent to saying this criteria is met. So if we convert from the language of sequence of partial sums to the language of infinite series, we get this result. But this is just a restatement of the definition that the sequence of partial sums will be convergent if and only if the sequence of partial sums is Cauchy. Now, why do we care about this? Well, it's not that this is so helpful. It's actually not very helpful in just taking a series and saying, does this converge or diverge? However, it can be very helpful when we go to prove some series convergence results. So we want to prove things, it's sort of like the Cauchy criteria for series. It's a helpful tool to have in your tool bag when you're trying to prove some things about whether, in this case, a series converges or diverges. So again, what I hope you take away from this video is that while series, there are some interesting things going on with series, at the end of the day, they're just sequences. So if we are careful to always think about our infinite series really as being some sequence of partial sums, then we have many, many tools at our disposal from previous videos to help us understand what's going on with that sequence of partial sums. And then once we understand what's going on with the sequence of partial sums, well, that tells us exactly what's happening with our series. We'll conclude this video here. In the next video, we'll begin looking at some convergence tests, which will help us determine when series converge or diverge. You may have seen many of these convergence tests previously in a Calculus 2 course, so our emphasis will not be so much on applying these convergence tests, but rather seeing how to use the tools of analysis, how to use the theorems, the Cauchy criterion for series, other results we've proved for sequences to help us prove that those convergence tests are valid.